Greetings at ULM, Gen Chem 1 students, Dr. Pryor here, trying to get us through the entire course. We're looking at drawing Lewis structures. We just talked about ionic bonding, then we went into covalent bonding, and then we got into polar covalent bonding. And now we're into drawing Lewis structures. And this is pretty easy. We just have to make sure that we follow a formula to get there. We need to sum up the valence electrons for the atoms. We have to account for any charge on the molecule. Um, we have to realize, if there is a polar covalent bond, and in this case, chlorine is more electronegative than phosphorus, so chlorine would have a dipole. Um, and so we'll look at the charges too, how to do the formal charges and write that up. I think the slides don't do it justice, and I'll show you a very simple way. We need to look at each atom as for its valence electrons and then figure out how many electrons are assigned to that atom. We don't do that with the octet rule. We actually share electrons, but now we're going to actually assign electrons in a bond to an atom just by dividing it by 2. We'll see that here in a second. But what do we need to know? The valence electrons involved in each of the atoms and how many there are. If we have more than one of the same atom, we need to multiply that valence electron number by, for example, chlorine has 7 valence electrons. We need to multiply 7 by 3, and we're going to get 21. And then phosphorus has 5 valence electrons, and we don't need to multiply that by anything because there's just one phosphorus in this molecule. It's probably going to be central. The less electronegative atom is usually the central atom or the atom that's in least number. So phosphorus is less electronegative than chlorine. Phosphorus is also less numerous than chlorine. It's likely the central atom. And we're going to get into electron domain geometry and molecular domain geometry. And what is the difference between molecular domain geometry and electron domain geometry? It's real simple, but you have to memorize it so you know it when you see it. So we know how many electrons total. There's 26 electrons. 26 electrons in this 26 electrons, right? And so what we can end up doing is put phosphorus central and the chlorines around it. And so when we do that, we put phosphorus in the center and we put the chlorines on the outside, and we try to space everything as far apart as possible. This really should be like a peace sign with the chlorines here and here, but we'll find out why we did this the way we did. We're also going to have to realize there are some lone pair electrons here, but we haven't added those yet. But we have 26 electrons. We put phosphorus in the center, and then we put the chlorines peripheral to the phosphorus all on the outside, and then we draw a straight line to at least connect them once, because we know they got to be connected somehow, and this is a good guess. We know that each line represents 2 electrons, 4 electrons, 6 electrons, so it's 26 minus 6. We have 20 electrons left over. We need to place the rest of the electrons somewhere. Well, we know chlorine has 8 electrons when it meets the octet rule. So we could end up adding at least 18 electrons around and split those up among the 3 chlorides. So if chlorine has to have 8 electrons, it only has 2 at this time. It only has 2 that it shares with phosphorus. It only has 2. Each one could get 6 electrons to make it 18 electrons. So let's do that. So I'm adding the dots around chlorine with the writing function. And so I'm putting 3 lone pairs of electrons, a total of 6 additional electrons around chlorine, total of 6 additional electrons, 3 lone pairs, 6 electrons. So that will end up, we'll have to subtract 18 electrons. And now we get 2 electrons left over. And we really don't have any way to put those electrons on chlorine. Chlorine's already got all the electrons it needs. And phosphorus doesn't meet the octet rule because it has 2, 4, 6 electrons. So guess what? The remaining 2 electrons have to be lone pair electrons on phosphorus. And that will be very important in determining the electron domain geometry. for example, if we were to determine the electron domain geometry, we have to consider, we don't consider all the atoms. If we want to figure out what the geometry is with respect to the molecule, we have to look at it from a central atom, from a central point, not from the chlorine's perspective, not from any of the chlorine's perspective, but from phosphorus, which is a central atom. The geometry is going to be determined with respect to the central atom with its connecting atoms around it. So we're looking at the electron domain geometry of uh, with respect to PCl3 with respect to the phosphorus, and we're looking at the molecular domain geometry also with respect to phosphorus. In the molecular domain geometry, we ignore treating the lone pairs as a group in itself. But with the electron domain geometry, we consider the lone pair of electrons on the central atom another group. But with the molecular domain geometry, we don't consider the lone pair electrons as another group, but we do consider them when they affect the shape and geometry of the molecule. What we're going to find out is electron domain geometry for this molecule is going to be tetrahedral. And we're going to run through this again through some slides. Tetra, and let me say hedral. Tetrahedral. Make sure you know how to spell tetrahedral. You want to be well learned. And we have molecular domain geometry, which we ignore the lone pair as a group in itself, but we don't ignore the effect of it. So we end up getting trigonopyramidal for molecular domain geometry. Trigonal, and then just like the pyramid of a three-sided figure, trigonopyramidal. And if you don't know what that looks like, I suggest Googling it or use AI to draw what's the difference between a tetrahedral structure and a trigonopyramidal structure. Here we have the same molecule. Its electron domain geometry is tetrahedral, and which is like a tripod and a central stick going up in the air, and the molecular domain geometry, which looks like a pyramid, a three-sided pyramid, which is called trigonopyramidal, and we ignore the electrons in the molecular domain geometry with respect to it being a fourth group. So we treat molecular domain geometry as if we have three groups, and we treat electron domain geometry as if we have four groups because we now count that lone pair for the fourth, right? So let's continue on. So we complete the octets all around the atom, which the chlorine we did. And I did this earlier, but let's repeat ourselves. We put the electrons around chlorine, which were 18 electrons. We did that after we connected the phosphorus and the chlorine together and assumed that that was 6 electrons. Then we placed 18 electrons around the chlorine to meet the octet rule because they're peripheral and they're electronegative and they're going to get the electrons. But we're left with 2 electrons, and we had only one choice, is to place those on phosphorus to give it a lone pair of electron as well. How many lone pairs of electrons does phosphorus have? It has just one lone pair, which consists of 2 electrons. And chlorine has 3 lone pairs, which consist of 6 electrons. And so 3 of them is 18 electrons. And so you can do the math. And we look at placing the remaining 2 electrons here. So we have a lone pair of electrons. And you're going to find out that PCl3 works like NH3, which is ammonia. They're the same structure. PCl3 and NH3 have the same electron domain geometry and the same molecular domain geometry. And there should be an octet around the central atom now, which is phosphorus. It's a less electronegative than chlorine. Remember, the electrons are being pulled towards chlorine. There is a dipole in this entire molecule, but we'll talk about that later. So all the electrons have been placed. All 26 electrons are now placed, and we can now determine the electron domain geometry or the molecular domain geometry or both. And what did we say? The electron domain geometry includes the lone pair for EDG, right? So that was tetrahedral, as I marked earlier. And if we were to talk about the molecular domain geometry, we ignore the lone pair, and that becomes trigonal pyramidal. Trigonal pyramidal. So two different geometries depending on whether we're talking about EDG or MDG. So think about that. Moving on, molecular domain geometry, just so we have more comprehensive view of this. Ammonia is, again, it's going to be the central atom. Hydrogen, we have three of those, although hydrogen is not necessarily more electronegative than nitrogen, but nitrogen is in less supply, so it's going to go in the center. Hydrogen can only form one bond where hydrogen can only hold 2 electrons. Nitrogen can hold up to 8 electrons and meet the octet rule. So we're going to put nitrogen in the center. Hydrogen can't be the center of attention. It has to be a peripheral atom, and it can only take up to 2 electrons. So a nitrogen has 5 electrons, but with 3 hydrogen bonds, it's going to be able to share 1 electron with each hydrogen to meet that total of 8 electrons. So the octet rule is going to be satisfied there. But if we go through that, we know that, again, just like with PCl, although we don't have as many electrons as we had in PCl, we had a lot more electrons to place, right? So if we were to draw this out, and hopefully this looks good on your screen, and now we have 2, 4, 6 electrons here. Ignore what I did here, back that up. Right now, I haven't put any lone pairs here. But we have 6 electrons with hydrogen and nitrogen. 3 of those hydrogens connecting to nitrogen, that's 6. We have a total of 8. We need to place 2 more, so we place an electron here and there. And now we have all 8 electrons, and we, again, will have the same geometry. The molecular domain geometry will ignore the lone pairs. It ignores it, and so we have a trigonal pyramidal system, just like a pyramid in 3 dimension. But if we go to the electron domain geometry, we have a tetrahedral, which is like a tripod for a camera. Okay, just think of a tripod with three stubs and a stick coming out, because when we talk about electron domain geometry, we have to consider, for the electron domain geometry, we have to consider the lone pair as another group, right? So this is VSEPR as well. VSEPR ties right in neatly with the Lewis structures and Lewis dot structures, and then the Lewis structures, and then you apply valence shell electron pair repulsion. And all that means is you want to space out pairs of electrons as far apart from each other as possible. And we do that with this by having them roughly 109.5 degrees apart from each other. But lone pair electrons are very suppressive and repulsive. I mean to say, they're more repulsive than the electrons in a bond. So lone pairs push the bond angle to something like 105 degrees. And this takes a lone pair of electron takes up more space than an electron pair between 2 atoms. So let me say that again. A lone pair of electrons takes up more space and is more repulsive than a lone pair or than a pair of electrons that are shared. So a lone pair versus a shared pair of electrons, the lone pair will have more repulsion, right? And that's VSEPR. We can spread this out tetrahedrally because there's 4 regions of electron density. If we think about the EDG, we have 1, 2, 3, 4 regions of electron density around nitrogen. We spread that out evenly. It can be anywhere from 109 degrees to about 105 degrees. Remember, because this is a lone pair of electrons and not a bonded pair of electrons that are shared, it's more repulsive and shrinks the angle. It has stronger repulsion than the electrons in a bond. So it influences the geometry just a tad bit more. Okay, so phosphorus trichloride, we already looked at that. And again, you can go through this. Again, it does the same thing. It's the exact same example with different atoms and less electrons, but it still gives you the electron pair geometry is tetrahedral, where you must consider the lone pair. And then the trigonal pyramidal, you don't consider the lone pair as a separate group. So you ignore it as a group, but you do not ignore the effect on the geometry. Okay, hopefully that's not too confusing. You do have a net dipole with the PCl bonds. You have 3 of those, and the electron density goes towards chlorine because chlorine is more electronegativity. You could look at your Pauling scale and calculate the electron negativity difference between phosphorus and chlorine is more electronegative. And so, interesting enough, and so we learned here about ammonia, which is NH3, and PCl3, very similar. So make sure you understand the difference between molecular domain geometry and electron domain geometry as well. So writing the Lewis structures, we can do this. Again, we know that hydrogen has 1 electron. We know that carbon has 4 electrons. And we know that nitrogen would have 5 electrons. So we would have end up having 10 electrons total here. And so we can put carbon as the central atom. Hydrogen can never be central. Carbon is less electronegative than nitrogen, so the electronegative atom should go to the outside, which nitrogen is more electronegative than carbon by just a little bit. And so we can draw a line, so we can end up taking up a line here and a line here. So we got to connect all the atoms for it to be a molecule, and then we're left with 6 electrons to place. And 6 electrons, well, we can place some nitrogen. Let's place them around nitrogen because it's the most electronegative. And then we can do that. And yes, nitrogen meets the octet rule, but we find out carbon doesn't meet the octet rule. Hydrogen is fine because it meets the duet rule. So the only thing remaining is we got to get 8 electrons around carbon. And there's only 4 right now, 2 electrons here and 2 electrons here for 4 electrons. So let's move 1 pair of electrons. We love in organic chemistry, we always move pairs of electrons. We always move pairs of electrons. And then here we move another pair of electrons. And we end up with this triple bond. Jiminy Christmas, what is that? It's a triple bond and it's very short. It's not very long and it's very strong and it's hard to break. That's actually a cyanide bond. And this can be an acid, and maybe not a strong acid, but sometimes it can donate the proton under certain conditions. We can do formal charges, and I'm not sure if the way they wrote this is correct. This is all correct here. So it's valence electrons, and then you want to figure out yeah, you also have to include the valence electrons. I don't really like this. I want to cross this out. They made it, this is right with half. For any bonding electrons, you need to take, if it's 2 electrons in a bond, you need to take half of it and assign 1 electron. But if we were to take this example of oxygen, carbon, and this species here, if we drew it like this, as opposed to carbon dioxide being drawn like this, let's draw carbon dioxide like this, but let's find out what the charge is on each atom. And to do that, we need to first figure out the valence electrons. We need the valence electrons, right? And then we need to subtract. Because now we need to figure out, does it have as many valence electrons as it needs? Is it short some valence electrons, or does it have excess valence electrons, which therefore will give it a charge of negative or positive? So it's valence electrons minus valence electrons that it should have, plus the bonding electrons. We'll call that Be, bonding electrons, right? And so valence electrons and any lone pair electrons that belong to the atom. So we also have to include lone pair electrons here if we're counting it up from the structure, okay? So let's put in the lone pair electrons on this carbon dioxide species that just looks a little different. It doesn't have double bonds between each carbon and oxygen. It's one single bond and one triple bond. And that is a possible resonance structure of carbon dioxide. And we're going to find out that if we put formal charges on things and we have an alternative way to move electrons that will make less formal charge on any of the atoms overall, that will be the structure we want to use, because charges on an atom are destabilizing. Sometimes we don't have a choice, and there are actual formal charges on an atom. But let's look at this a little bit closer. Um, I made a mistake here. We don't there are no, we don't have no electrons here. Get rid of that. We have just 2 electrons here. And so we look at this oxygen. Let's look at this oxygen. We know that the valence electrons on that are always going to be 6 on oxygen. And then we can count up that we have 2, 4, 6. We have 6 valence electrons again. And now we have to add any bonded electrons, divide it by half. We do have this bond here, which is 2 electrons. So we have to take 2 electrons divided by 1/2 is just 1 electron. And what we end up getting is a -7. We get a or excuse me, we get a -1. 6 minus 7 is a -1. We have to be careful how we do this. We add the valence electrons plus any of the bonded electrons, half of the bonded electrons, and we get 6 minus 7, so we get a -1 on here. Now we're going to do the same for carbon. What's the valency of carbon? It's going to be 4. So we're determining the formal charge on carbon if there is one. We know that this oxygen has a -1. This oxygen is different, so it's going to have a different type of charge on it. So let's see what happens when we get to that one. We're on carbon now, and so we know there's got to be 4 valence electrons on carbon. So how many does carbon have around it? Well, it has, it definitely, we look at this and we say, okay, there's 2, 4, 6, 8. So it's got shared bonded electrons. Bonding electrons is going to be half of that. So we know that half of the bonding electrons here, half the bonding electrons. So we know that it doesn't have any electrons floating around. It doesn't have any free electrons. This has over 6 free electrons. So we don't have any valence electrons that belong exclusively to the atom. So we don't have anything to put in here. So carbon has 0 here. And then we have carbon is bonded to 8 electrons, but only half of them belong to carbon. And that's 8. 8 divided by 2 is going to be 4. So it's going to be 4 minus 4, which is going to equal 0. And so carbon is going to have 0 formal charge on it. Now let's go to oxygen. And now we got to calculate this with respect to oxygen. And it does have 2 lone pairs here. Or no, excuse me, it has 1 lone pair. It has 2 electrons on a lone pair. So what is the valency of oxygen? Oxygen is again 6. So we're calculating the formal charge on the oxygen on the right-hand side. We know that's going to be 6. So how many electrons belong to oxygen exclusively? Just 2 because of the lone pairs. It only has 2 electrons that belong to the oxygen itself, so it has 2. But in the bonding, we have to add the bonding electrons and subtract that from the valence number that we find from the periodic table. So it has 2 electrons that belong exclusively to oxygen, which only are on oxygen. There's 2 electrons. Then we have to count the bonding electrons. We have 2, 4, 6. So we have to say half times 6 electrons. We have to say half of those. And that's 3 plus 2. That's going to be 5. So it's going to be 6 minus 5. We're going to get a +1. We're actually going to have a +1 on this. We're going to have a +1 on here. So if we compare having 2 double bonds on carbon and with 1 oxygen, another double bond with carbon and oxygen, we do the same thing and we see that the formal charge is 0 for every single atom. But if we move a couple of electron pairs over here and put another lone pair over here, as we did with 3 lone pairs of electrons, we have 6 electrons all by themselves, only a single bond here and a triple bond here. And if we go back to having a double bond and a double bond here with only 4 electrons or 2 lone pairs on each oxygen, we end up with no charge, no formal charge. But if we move the electrons and we place our electrons in the wrong position And even though we meet the octet rule, we still have to acknowledge that we drove the energy up of the atom because now we have charge separation, a negative and a positive one charge separation. That's energetically unstable. And if we have an alternative form, we of course want to use this form because we get no charges on the individual atoms, where here we get a -1 charge on oxygen and a +1 charge on this oxygen, and we want as little formal charge on there as possible. So if we were to look at some other examples, we can do this and we can figure out that nitrogen here will end up having a -2. We know, and carbon will have 0, and this one will have a +1. And then we can compare the other another version of it with a -1, a 0, and a 0 here. So this species has it has two formal charges of a -2 and a +1. This one only has a -1. So I'm going to tell you that this one is more stable. This one is more energetically stable than this one here. This one has more charge separation. But they have another situation, and let's do this one. This is going to be nitrogen triple bonded to carbon with the sulfur here, right? And then we have a lone pair on nitrogen. Carbon has no lone pairs, but now we're going to have 3 lone pairs on sulfur, just like we had with oxygen. And so we can do the calculation here and figure out what's the formal charge on nitrogen. Well, nitrogen has 5 valence electrons, so let's do nitrogen as it's written, right? And so then we want to subtract, well, how many bonds are actually on nitrogen that belong to it? Only, not bonds, but electrons. How many electrons actually belong to nitrogen and are not shared? Oh, that's only 2 because it has a lone pair. Then we have to add up the shared electrons it has with carbon, which is 2, 4, 6. So we need half of the electrons from the carbon nitrogen bonds, which is 6. And we're going to end up having 2. We're going to have 2 plus half of 6 is going to be 3. So we're going to have 5 minus 5, and that's going to end up equaling 0. So we have a 0 charge on nitrogen. Carbon is going to be 0, and maybe you don't see it, but let me show you. Carbon will end up being 0. It'll be sulfur that determines is this structure, which is partially blocked by my small head. We have to say carbon has, excuse me, as soon as I get the pen to work, we know that carbon has 4 valence electrons, but now we have to subtract the amount of electrons that belong to carbon in the atom plus half of the bonded electrons. Well, carbon has no electrons that simply belong to it, so that's 0. But now we got to figure out how many bonds does carbon have. It has 1, 2, 3, 4 bonds. It has 8 electrons in shared bonds, and it only needs half of those. So we have 8, half of 8 is going to be 4. 4 minus 4 equals 0. So we should know that this is 0 on carbon. Now the hardest one is sulfur, and it's a fun one to do. Sulfur is just like oxygen. So to calculate the formal charge of sulfur in this specific species. So to calculate that for sulfur, so sulfur equals, we know sulfur has 6 valence electrons. Now, how many electrons does the species have for sulfur? Well, we know it has 2, 4, 6. It has 6 electrons that belong completely to it, but we have to add the bonded electrons. And the bonded electrons that we have available are just 2 with carbon. So we know 2 electrons are shared with carbon. So we have 6 plus 1/2 times 2, which is 1. So it's 6 minus 7. And so we have a -1 on sulfur. So we have a -1 on sulfur. So in that case, we look at this and we can say, well, a lot of these are kind of equal. And which, the middle structure is the nitrogen is more electronegative. And see, here's the problem here. Okay, nitrogen is is a little more electronegative than carbon, but sulfur is the most electronegative if we look at the electronegativity scale. So when we compare these different resonance structures that can have a different um, array of electrons and still meet the octet rule, then we have to look at the formal charges, and we want to put the electronegativity, we want to put the negative charge on the most negative atom. And the most negative atom here is sulfur, okay? So putting a -2 on nitrogen, that's a bad idea. Putting a -1 on nitrogen may be a bad idea. We don't know. Carbon is neutral. That's good. But then in sulfur, I said over here, and when I evaluated this third structure, which is what I did up here, sulfur ends up with a -1. Carbon has 0. Nitrogen has 0. So we put a negative charge on sulfur. And sulfur is more electronegative than nitrogen and carbon. So be it that sulfur is a little more electronegative, this might be the best structure. I would say this could be the very best structure here. This one is actually the best. Review the slide if that doesn't make sense. So following the rules, there are 2 Lewis structures for ozone, O3. However, it doesn't agree with what is observed in nature. Both OO bond lengths tend to be the same, probably because of resonance. We end up with resonance. And so ozone, we have shared electron density throughout the molecule. And so we use multiple resonance structures that are equivalent. And so some cases there's not a best resonance structure, they're both equal. We saw a case where putting the negative charge on sulfur was the best thing to do, but we can have these are equivalent. They're equivalent and they're a mixture of both. And in fact, we can actually draw this. So there is no, if we did the formal charges, it would end up being the same, okay? And we're looking at resonance structures. And resonance structures are achieved by moving what? We move lone pairs of electrons around to different locations. We always move electrons in what? We move electrons in pairs. 2 electrons are moved at once. Hardly ever a single electron unless we're talking about radicals. So when you go to organic chemistry, you're always going to be moving pairs of electrons to do resonance structures until you get to radical chemistry. And that's just a small part of organic chemistry 1 and 2, but important. So you want to move 2 electrons, not just 1 electron at a time. And so if you were to do that here, you move electron here, and then that would cause this electron to go, a pair of electrons to go there. And you would get this other structure, and you would draw a line between that. And you could do that you could move these electrons into forming a double bond here, and you can move these pi electrons onto oxygen exclusively to be a lone pair. And you can do that all day. That's kind of the resonance game. And it turns out that the formal charges equal out, so both resonance structures are good. So it's going to be both. The actual molecule is going to consist of both resonance structures, unlike the other example where we tried to get the negative charge on the most negative atom. This one's a little bit different. And if I were to draw this, I could do something like I can try to make a hybridized version of this. And I could have a dashed line that shows the electron density is shared. The electron density is shared throughout the 2 bonds between all 3 of the oxygen atoms, and the electron density is distributed symmetrically around the molecule. Okay, and they're trying to show this color analogy, which is kind of cool. So the bond lengths end up being equal. They're equal lengths because the electrons are equally shared to, and resonance explains that. So interesting. We have a situation where we always move pi electrons or lone pair electrons. Pi electrons are in a double bond. We saw lone pair electrons earlier, and we moved lone pair electrons exclusively. But pi electrons, although are shared by 2 atoms, they can be moved. Pi electrons can go here, and then the pi electrons can go here, and then the pi electrons can go here. Okay. Now, a single bond is called a sigma bond. If we were to, like in ethane, or if we were looking at ethane, these are all sigma bonds. No double bonds whatsoever in ethane. They're all sigma bonds, all sigma bonds. There's no resonance to speak of in ethane. It's a very simple hydrocarbon. Um, we could remove two electrons and introduce a double bond if we got rid of two electrons, and then we would have a pi bond. But these are sigma bonds, and a double bond contains a sigma bond, and it contains a high energy pi bond, which is higher energy, and it's the electron that will move throughout the molecule when we draw our resonance structures. It's at higher energy than a sigma bond. And so all I did, and I can do this again, I can move pi electrons. Pi electrons have more energy, so they can move more readily, right? More energy, more movement. So I move the pi electrons again. And so we often draw this species here, or we don't always draw it this way. We sometimes draw it as a dashed line, not as a solid line. And that's pretty much the same thing. Excuse me, sorry. Very poor drawing tonight. So these electrons are also called, the electrons that can move are called delocalized electrons, and they can move onto multiple atoms. Localized electrons are stuck with one atom. They cannot move. That's when we talk about ethane, before I draw the ethene. Um, Sigma bonds in a methane has localized electrons. Methane has no delocalized electrons. And so that finishes that part of chapter 8. Chemistry 1007. Thank you for listening. I'll be back with a little bit more for chapter 8 to finish that off.